Screening by barriers. There are various methods in textbooks to calculate the acoustic screening effect of physical barriers. The main principle of using barriers relies on the strategy of blocking the line of sight from the source of noise to the listener location with a high mass material construction. You can see there on the right-hand side there's a bank of chillers on the rooftop of a building, and the height of the barrier is higher than the highest point of the chillers. Therefore, it's an effective barrier blocking the chiller noise to a receiver location that is most likely below the chiller enclosure. If the source is screened by blocking the line of sight, the sound is forced to take a longer route and bend around the screen edges by diffraction to reach the listener. The effectiveness of the screening depends on the path difference, which is the distance that the sound has to travel by bending around the top of the barrier compared to the direct line of sight between the sound source and the receiver location. The attenuation provided by the screen construction itself. So the screen or the barrier has to have enough mass to stop sound actually being transmitted through the material itself. The size of the screen in relation to the wavelength of sound. The screen size or the dimensions needs to be much larger than the wavelength of sound that we're trying to block. For instance, the wavelength of sound at 63 Hz is 5.4 meters. Therefore, to effectively block low frequency sound at 63 Hz, we have to have a barrier dimension that is much larger than 5 meters in all directions. If the sound is able to travel more than one way around a screen, so over the top of the screen and around the sides of the screen, the components of sound reduction are estimated separately and then are combined by decibel addition. Let's look at the critical considerations of barriers. So we have to consider the barrier dimensions to get the maximum path difference. So for instance, the higher the barrier, the greater the path difference between the source and receiver. It must have sufficient mass to prevent noise transmission through the barrier itself. And a rule of thumb is that the barrier mass should be at least 25 kilograms per meter squared. That is the equivalent of 2 layers of 9mm compressed fibre cement sheet. We have to ensure that there's no gaps or cracks or holes in the barrier, otherwise sound will just short circuit through these gaps and cracks instead of through the material itself. We also have to consider the barrier dimensions compared to the wavelength and sound to make sure that the width and height of the barrier is large compared to the wavelength we're trying to block. Let's look at a two-dimensional example of screening by barriers. So we have a cooling tower here sitting on the top of a building, and the barrier is shown by this orange line here. First of all, we have different zones, which we call the bright zone and the shadow zone. If we have a neighbouring residential building and the window from an apartment has a direct line of sight to that cooling tower, it is considered to be in the bright zone. So there's no beneficial screening provided by that cooling tower because the barrier is not high enough to block the line of sight. On the other hand, at an apartment lower down in the building, where the window has a line of sight that is blocked by the barrier, we are going to get beneficial screening. The path difference here is calculated by A plus B2 minus that direct line of sight distance S2. So in this case, we do get beneficial screening to this window location here. Here's an example of a barrier calculation which takes into account the dimensions of the barrier and calculates the screening effect across the different frequency bands from 63 Hz to 8 kHz.
This is a demonstration of the acoustic benefits you get from an acoustic barrier. What we're going to look at is the configuration of the shadow zone as I've previously presented. So this configuration here on the bottom right, where a noise source is blocked from a receiver by an intervening barrier. So the calculation involves the following inputs in these yellow cells, where you need to know the receiver height, in this case 2 meters, the source height, here 3 meters, the source distance to the barrier, the horizontal distance 3 meters, the receiver distance to the barrier 15 meters, and the barrier height itself 5 meters. So I've used the Beranek method to do the barrier attenuation here, which calculates all the different path methods, the path differences, and also takes into account the Fresnel number. So you can look that up in Beranek's book, Noise and Vibration Control. I use the 1988 edition. So in this configuration here, where we have a barrier height of 5 meters, it is blocking the line of sight between this cooling tower and the receiver location, because the receiver height's 2 meters and the source height is 3 meters. And in this case, you can see for the different frequency bands, it gives the attenuation of 9, 11, 14, 17, 20, 23, 26, and 29 decibels. Now, if we experiment with the height of the barrier, we can make the barrier higher and make it 6 meters. You can see the benefit of the barrier improves. So in this case, from 11 to 32 decibels. Now, in the case where the barrier height is lower, you can also see we'll go to 4 meters instead of the original 5. It goes from 7 to 24 decibels. Now, in the case where you make the receiver height and the source height the same, so we'll make 3 meters for the source height, 3 meters for the receiver height, and you make the barrier height just about equal to the source and receiver heights, you can see that you get an attenuation of 5 dB across the frequency range. And this is considered to be the crossover zone between the shadow zone and the bright zone, where there's the grazing incidence. So this is sort of the minimum amount or the maximum amount of attenuation or benefit you'd get in the shadow zone when the source and receiver heights and the barrier heights are equal. So obviously the intention here is to maximize the benefit of the barrier. So putting it back to 5 meters here, keeping a source and receiver height of 3 meters, you can see that there is still a significant acoustic attenuation achieved across the frequency bands. And as you can see, there's more benefit in the higher frequency bands because it's where the wavelength of sound is smallest compared to the barrier dimensions. Thanks.
So just to summarize, the rules of thumb for screening by barriers: for effective barrier design, you need to block the line of sight, locate the barrier close to the source, maximize the path difference to the receiver location, and use other buildings and other topographical features for screening. In that case, you might not need to include a barrier if you have other buildings in between that can act as barriers for you.